Hello, welcome to session 2. Hello, welcome to. So I hope you guys can hear me today. Okay, great. So hello, Sabi. So good. So today at least it's working. So that's good. So I think people are having trouble with installing tidyverse. That's okay. Because I don't think that we'll reach tidyverse today. So fortunately, Ben and Ben had some troubleshooting. So we'll include all of this troubleshooting in the preparation for next time. And Yura will also help you. And also personally, I'll help you guys install tidyverse if other people have problem. Yeah. So don't worry about it for today. So it's good that at least we are 1 week ahead, or at least one session ahead. So the installation issues can be sorted out before the next session. Yeah. Okay. So I think we can start now. It's already been 2 minutes. Yeah. So good afternoon. And today we'll actually move beyond theoretical discussions. So last time, we discussed very theoretical things like what are vectors, what are different kind of vectors, and all that. We'll do a revision, but today we'll at least get to some things that I think you guys were looking for when you took this course. So things like plotting and statistical analysis. Yeah. So and just let me know if things are not very clear, but we'll try to go as efficiently as possible. Yeah. So just one thing about the course organization. So all the links for YouTube sessions as well as information will be now available on the GitHub page for the course. So because there are some people who are attending because of social media, and I don't want to keep spamming people with the YouTube link. So just keep checking this thing. The next session is on Thursday, same time, so 5 p.m. Belgium time. And the information about all the next sessions will be here. Also, there is a YouTube playlist. So all the sessions will be listed there. So if you just go to that one place, the YouTube playlist or the GitHub, you'll find everything there. Yeah. Okay. And another thing about the course timeline is that we'll have 6 sessions on what we intended to do, and then I think we'll add one more session, and this will be more about how to present your code to others rather than writing code. So you have written a piece of code, but then how do you share it with others? How do you make it reproducible? How do you make it accessible? So we'll also be building a website. We'll be building a practice website where you can distribute your not just your code, but you can also have other people interact with your code. You can have other people play with your data. Because sometimes when you do some analysis and then you just give the analysis, others want something new to be done. And if you make these kind of interactive websites, then they can do it themselves rather than them coming back to you. So we'll include one more session on these kind of things, how to share and make your code accessible. Okay. So with that, I think we'll go for a quick uh, revision of what we did last time. So I'll make my screen a bit bigger. Right. So I mean, last time we started with the introduction to RStudio, and I hope that it's a bit more familiar, the design. So you have your file, you have your console, uh, then your environment, which are your current variables, history, whatever you typed in your console, and then plots. We didn't plot anything last time, but today we'll do so. So we'll be using this thing a little bit. Also, this side here, the lower right shows help. Yeah. And so again, I'll just like last session, I'll be live coding. So I have a file here which I'll use for reference, but I'll be coding with you. And if you guys feel at any time, just pause the video. If you want to type something, I'll go slowly, but if it's a bit too fast, just pause the video, and because you can come live anytime and watch it as much time as you want. Yeah. Right. So so we saw that R is really good in doing simple calculations, right, and storing the results, right. So let's say if you just want to do very, very simple calculations and store your results, so you can have my variable, right. So this is just a simple variable, and to assign a value to a variable, we use this kind of assignment operator, right, which is directional. So whichever way the arrow is pointing, that's where the information flows, right. So you can have this way. So now the result of the operation 4 plus 4 gets stored into this variable that we are calling my variable, right. And variable names in R are written without quotation marks. That's how R knows that it's a variable, right. So in this way, you define a variable and you store a value, and all the variables that you have defined show up in your environment, as well as their values. But if you also want to see their values, you can type their name. And instead of typing the name of a variable, it's better to let R do the work for you. So just type a part of the name, and then R will give you some suggestions beyond which you can press just tab. And to run a line of code from the editor, that's where we are writing right now. This is where you save your R files. You press Command and Enter, right? Or you can use the button here which says Run, or you go to Code, Run selected lines. Yeah? So these are the three ways of running a piece of code. And anytime a piece of code is run, it goes to the console and it's executed there. If the result of the execution is saved in some kind of variable, you do not see the result. Otherwise, the result is shown here. And if the result is shown here, it's not saved anywhere, right? So it's not put in memory. Right? And these are simple scalars. So they just have a single value. But you can also have a collection of values, and these are called vectors, right? So vectors are collection of values, and you can have four kinds of vectors, and we'll just quickly go through them, but we'll also look at a few additional operations which we can do on these vectors, right? So the first vector is a numerical vector, which is a collection of numbers. So we can define a numerical vector called my numbers, and we can just give it a few numbers. So this, to make a vector, you have to make a collection, and the way to make a collection is to use the function C. So C is concatenation, combine, collect, however you want to call it. C, then round brackets, and every element of a vector has to be separated by a comma, right? And this would then make a vector for you. So let's make a vector of random numbers. Here we are defining numbers, but let's get some random numbers. So how do we get random numbers? So last time, for one of the sessions, I had said that if you do not know how to get if you do not know about a function, if it exists or not, you can do search with double question mark. And the thing is that this search actually works, but and you guys can try it, but there was a bug with the previous installation of RStudio. So if this double question mark based help does not work for you, then you just have to upgrade your RStudio version. Yeah, this also happened to one of the sessions last time. So let's say that I don't know what is the function to get random numbers. So I want to search all the help pages that R provides. So I can do double question mark random and execute it. Of course, you'll have to execute it, right? The R will take a little bit of time because it's searching all the help pages. And then you will find different functions as well as different packages. So before this, colons are the package name, then the function name, in which somewhere or the other the word random is mentioned. It could be in the title, it could be in its explanation, right? Most of the time you would want to go and look into base. So base is functions that come pre-installed in R, right? And these functions are most possibly the simplest to use. So here is one of the function called sample, right? So sample is a function that gives you random values within some range, right? So sample takes a sample of specified size and gives you some values, and these values can be with or without replacement, right? So let's make some random numbers. So random number, right? So this random number is a variable name, right, that we will define so that we can store these random numbers. And then in the help pages, you can see how to use this function, firstly, and secondly, what kind of arguments does it need, right? So let's make a collection of random integers. So let's use sample.int, and it needs n, where n is a positive number, the number of items to choose from. And if this is not very clear, you can always go down to the examples. Help pages always have some examples here, and here they will tell you how to exactly use it. So here is like one kind of example, right? So again, we can type the name of the we can type a part of the name of the function. Let R autocomplete it for you. Choose sample.int, right? And once you're inside the bracket, if you again press tabs, it will give you the different input options, right? So, and it will also give you explanation for each. And as we said last time, you can either put your inputs by position, so you can match the position, or you can match by name, right? So we can say n. So n was the range, I think. So positive number, the number of items to choose from. So what is the range for you, right? So let's say that I want random numbers between 1 to 100, right? So I say 100. So that means the range is 100, right? And then we can say size. So giving the number of items to choose. So let's say we want 10 random numbers, right? And replace. So should they all be unique? If you want them all to be unique, then you can say replace equals to false. Or if you don't care about it, then you can say replace equal to true. So you can decide what kind you want. I'll say replace equal to true. And now let's see what the random numbers are. Right. So here we get a range of numbers. They're all between 1 to 100, right? And I did say that replace equal to true, but still they are all no, unique numbers, right? So this is one way of getting random numbers. I'll just show you another way. And for another way, we will search for normal distribution. So this is just a random numbers in which it's easy to get random integers, but you can also get numbers with normal distribution. So we'll search for the function first. So double question mark normal distribution, right? It will search the help pages. And now let's go to base. Is there a function that will help us? No, but in stats, in this package stats, the package stats also comes pre-installed. So this thing has a normal. And if this double question mark is not working for you, again, it's because of the old version of RStudio. Then just search for the name of the function that we are putting here. And to search a function by name, you can do question mark, so single question mark, then name of the function, right? So you could do normal, right? So it's stats package, the name of the function is normal. So to search for this function, you can do question mark normal. Right? So now this is how to get normal distributions, and we can use R norm. So R norm is random distribution, random numbers distributed normally, right? And here the attributes are n, mean, and standard deviation. So n is the number of observations, so the number of items that we need, the number of numbers that we need. What would be the mean of the distribution, and what would be the standard deviation, right? So let's make a random distribution which is normally distributed. So norm ran numbers. You can give the variables name whatever you like, right? But just give them descriptive names, because as we said last time, a good code is also a code that's easy to read, right? So easy to understand, easy to interpret, and you can go back to it after a few years and still interpret it, right? So R not the name of the function, then within the function we press tab, we get the attributes. And another important thing, so here you see that by default mean is 0 and standard deviation is 1, and n doesn't have a default value. So in a function, if something does not have a default value, then that is something that you have to provide as an input. Other arguments which have default value, you can leave them, you don't have to define them, they will just get the default value. So for example, we'll just run in the console. If we run our norm and we say mean equal to 5, right? We do not specify n. N is something that is not defined by default. Then what we will get is an error, and it will say that n is missing, right? But if we run our norm n equal to, let's say, 10, right? We do not define what mean and standard deviations are. We still get 10 values. Right? And for these 10 values, the mean will be 0 and standard deviation will be 1. Right? So if something is not defined by default, then you have to define it, otherwise it will throw an error. Or for something that is defined by default, you leave it. Right? So we'll say n equals to 10. Right? And then it's okay for me to be mean to be 0, standard deviation to be 1. If you guys want to play around, you can change it, no problem. Right? So now let's see, what do we get? Right? So we get 10 different numbers, right? And you'll see that we had just called this function a few seconds ago, and these numbers differ, right? And that's because we created random numbers. It's a random sampling, so of course the numbers will differ. But technically a computer is making a random number, right? So the numbers are never really random, they're actually pseudo random. And it's also a pseudo random algorithm that builds it. So if for the sake of reproducibility, you want to have random numbers, but you want to have the same set of random numbers each and every time, right? So you don't want to, you want a distribution that behaves like random, but you want the same numbers again and again. Then what you have to do is, before calling any function that generates randomness, you can set a seed. And seed is a number that the pseudo random algorithm uses to build on random numbers. And if you are interested, you can go and search on this, on how it's exactly done. Even I don't know. So to get the same set of random numbers, you can just say set.seed some number. So 1, 2, 3. Yeah. So as long as you set the seed to the same number, the pseudo random algorithm will run exactly the same, and it will give you a distribution that behaves like random, but the numbers will be the same. So let's do that. So Let's set seed to 123. Let's execute this line and then make 10 new random numbers. Right? Now, when you run it, you see that you get some kind of random numbers. Right? So you have to call this set.seed again every time, before every time you run your random function. Yeah. So we run it again, the set.seed, 10 new random numbers. But you see, these 10 new random numbers are exactly the same as the previous ones, right? So you get a distribution which is pseudo-random, but the set.seed is going to define this distribution. And I think, but I might be wrong, that these 10 numbers will be the same across operating systems. Although maybe people who are working on different operating systems can check and see if they get the same 10 numbers. Right? So let's run this one more time, but without calling this command set.seed, and let's see if the result now changes. Right? So now I again call this random number function, but I did not set the seed, and you see that the new 10 numbers that I get are different. Right? Let's do it one more time, one last time. So we set the seed this time, we call it, and we get back our original 10 random numbers. Right? So this is something that you might want to think about for writing reproducible data, especially if you have some kind of a call to random function. And if you really want it to be completely reproducible, you would want to set your seed, right? So so this was just some numerical vectors and how to get some how to make random numbers. So this is the functions, and how to get reproducible random numbers, right? So just as a summary for a function, use the help pages. They're really helpful. You can use Google, and anything that is not defined by default has to be defined. The things which have been defined by default, you can leave them if you like, and you can call a function by matching the name of the argument, right? In this case, you could also just write rnorm 10. This is matching by position. So because the first position, the first argument here is n, so just calling rnorm 10 will mean n equal to 10, right? So that you can also do that, and that is matching by position, right? So this becomes a numerical vector, right? It's a collection of all numbers. Okay, so for Mac, it's also, I'm also on Mac, so at least for me and Sabine, it's the exact same numbers. So that's good. Okay. So the next thing would be character vector, right? So character vectors would be a collection of characters. So let's say, so my characters, we can make them a collection of some greetings, right? So let's say, hello, hi, French, bonjour, if it's correct pronunciation. And we can also say Jama, right? So we make a collection of 4 different greetings, right? And we put them in a vector called myChars, right? So now we have a variable which contains 4 different characters. So yeah, each element in a character vector is also called a string. So just to, so each element. So the thing with character vectors is that last time I didn't cover it. You cannot, of course, do numerical operations, right? Because adding a number to alphabets doesn't really make sense, right? So it will throw an error. But is there something similar to an addition for character vectors? So let's say if I want to add world, so I want to say hello world, hi world, bonjour world, hello world. That means I want to add the string world to everything. So is there a way that it can be done, right? Which is similar to an addition for numerical vectors. So the addition for character vectors is a function which is paste. So, and if you guys want, you can look at the help page of paste. So let's do that. Okay. So paste is, so as it says, it concatenates vectors after converting to characters, but this is the most important line. If the arguments are vectors, they are concatenated term by term to give a character vector result. So how does it work? So let's say we want to add world to each greeting, right? So we can say paste, right? So let's see how it works. So you can see that it actually doesn't specify any argument. It just says 3 dots. What does it mean? What it means is that you can give these 3 arguments can be any character vectors, and you can give them as many as you want. So you're not restricted to 2 vectors, you're not restricted to 3, you can give it 10 vectors. So these 3 means any number of vectors which are of this type, and in this case the type that it wants has to be character vectors. So it can be 1 or more, so there is no upper limit to how many vectors you can pass as an argument. So it's open-ended, right? So if you have my cars, so to add to the greeting, right? So first we have to put, so we want um, to add world to every greeting. So we first put the character vector, right? And then the second thing that we put is world, right? So now we are passing 2 vectors to this function called paste. One vector is our collection of greetings, and the other vector is world. I mean, even though world is a single element vector, it's a scalar, it will get recycled. And recycled will mean that it will be used, this thing will be used for each and every element separately, right? So that's recycling. Yeah. And we can, so again, we are using the function paste, and it says that the default separator, so separator, we can see that this is the thing that will separate the terms. So the default separator is a space, and we will leave it because we want uh, to have the greetings connected to the world with a space, right? So once we do that, so you see we have added the string world to every greeting, and at the same time we added a space, and this is what the function paste does. So this paste is the equivalent of an addition but for character vectors. Paste 0 is just a special function in which the separator has been defined to be nothing. So if you put paste 0, right, if you just change it, then you'll see that the separator is gone. So paste 0 is just 0 space. That's about it, right? And you can also give default spacings. So let's say if you want to put underscores or a dot, it doesn't matter, but some new character in between the 2 terms that you are connecting, right? Then you can specify them with the separator argument, right? So we can say underscore, right? So that would mean take the terms from the first vector, take the terms from the second vector, combine them together, but separate them with an underscore. And once we do that, this is exactly what we get. The world is added to each and everything, but also an underscore is added, right? You can also pass numbers. It's completely fine, right? Because what it will do is it will make the numbers into characters first. So it will not treat them as numbers because the argument is either a character vector or something that will be converted to a character vector. So if you pass a non-character vector, it will get converted into one, right? So let's say if we pass paste, yes, let's pass some numbers. So we have 4 greetings, right? So let's pass a vector 1 to 4. So 1, 2, 3, 4. Yeah, so there are two ways of passing it. Either we can write C 1, 2, 3, 4, or we can use the shorthand notation in R, which is 1 double colon 4, right? So 1 double colon 4 is 1, 2, 3, 4, a vector which is 1, 2, 3, 4. So it's a range, right? And we say, okay, our separator will be, let's say, dot. Yeah. So once we do that, you see, now it has taken the first element of my chars, which was hello, added the first element of the other vector and separated them with a dot. Then it did the same thing for the second, it did the same thing for the third, and then it did the same thing for the fourth, right? And this is actually a good place where to showcase some kind of recycling. What recycling means is, if you are doing an operation between two vectors which are not of similar length, right? So here they are both of length 4. So this thing has 4 greetings, this thing has 4 numbers. Then the operation is okay, it's 1 to 1. But let's pass a smaller thing. So let's pass 1 to 2, right? So this vector mycars has 4 greetings. 1 to 2 only has 2 numbers. What R will do is, let's see what it will do. So what R has done is it has recycled. So first, it combined the first element of both the vectors. Then it combined the second element. Then it went to the third element, but it didn't really find a third element in the second vector, right? It's only 2 numbers, 1 and 2. So it didn't find a third element. So it went to the start and it took the first one. Yeah. So this is called recycling, right? So if you pass something of non-matching lengths, then it will do recycling. And this is the whole concept. So this is what it says here. Vector arguments are recycled as needed, with zero length arguments being recycled to nothing, right? So these are just an example of how you can add with character vectors and what are the different variations and how recycling works, right? So there are many other string operations you can do. For example, you can extract a few strings and all that, but we won't go into too much detail into string operations because for data analysis, that's not something that we do a lot. But if you are interested, I think you can either use Swirl to learn about more string operations or via Google, right? So, and one other thing that we should at least discuss is how to increase the length of a vector. So you have defined a vector which is of size 4, right? And you want to now add, let's say, 3 more greetings. So 3 more greetings in 3 other languages, right? So to do that, you have 2 options, right? You can either write down all the greetings again. So let's just copy paste, right? You can, let's say, we do Hindi, we do Japanese, and we do not know a next one. So let's do Japanese again, but how they say on the phone. Okay. So if we want to, let's say, add 3 more greetings, we can do it like this. And if your code is running outside your view, then it's always good to take it to the next line. And the way to take it to the next line is to press and enter after the comma. So not before the comma, because comma is separating individual elements, But after the comma, before you start the next one, you can press enter, and actually R will put it right underneath the start of the same vector. Yeah, so it also is good for tracking things. So anytime your code becomes too long to read, just do this. It's really nice visually, right? So this is one way that we can define this vector. But the thing is, we already had these 4 defined into a variable beforehand, right? So we can add elements to a variable by just passing the same variable, right, as a part of the collection. So what we can do is, instead of saying these 4, we just do this. Yeah. So what this means is that we take the collection of 4 greetings and we add these 3 to them, we combine them all together, and the result we store into a new vector. You can also replace the old one, but anyway, yeah. So as always, a variable is a shorthand for whatever it stores. Yeah. So this way you can increase the size of the vector, so you don't have to keep on retyping it again and again. Just make it into a new collection with the new elements that you need. So once we do that, right? So let's see now. So now you do get a new vector with the additional 7 greetings here added up, right? So this would be the way to add new elements to an existing vector to increase the size of the vector, right? You just make it part of a new collection. Yeah? And the next one is a logical vector, right? So logical vector are typically the results of a logical operation, which is a conditional operation, a comparison operation. And logical vectors are pretty simple because they only have 2 values. So they only have true or false, right? And so let's do that. So let's try to see, when we made our random numbers, let's see how many of them were greater than 0. Yeah. So we made a random number with mean of 0 and standard deviation of 1. So we'll have some positive values, some negative values. So if we compare this a numerical vector to 0, we'll get a logical vector where each number individually has been compared to 0, right? And if it's greater than 0, if the condition is satisfied, then it's true. If the condition is not satisfied, then it becomes false, right? And very importantly, the um, the advantage of a logical vector, or one feature of a logical vector, is that true is uh, stored as 1 and false is stored as 0, or treated as 1 and 0 respectively, right? And this is really, really useful because you have to do a very simple operation like to sum on the logical vector. Sorry, we didn't save it. So we can say my logical. We save the result. Right? So once we add up them, whatever are the number of positive or the number of true, we get that as a result, right? So we had 5 numbers which were greater than 0. That's actually a perfect coin toss because uh, by random distribution there should be 5 above and below, right? 0. So this actually helps us to get more information about the logical vectors. For example, let's say, what is the percentage of success? So what were the percentage of numbers which were greater than 0 in this numerical vector, if you want to find that, right? So you could use 2 functions which will help you. So first would be sum of my logical, which will give you the number of success or the number of true elements and then you need the total number of elements, which you can get from the function length. Right? So length will give you what is the total number of elements, right? And when you divide these two numbers together, you will get the percentage of success. If you really want percentage, you could combine all this and multiply by 100. So these are the kind of operations which become really useful with logical vectors, and also with subsetting, which we'll come to next. Right. So logical vectors are really important for subsetting. Yeah. Let me just check about logical vectors. Yeah, that's about it. Yeah. And the last vector, which we'll use a lot today, and actually it's one of the strongest feature, I would say, of R, is the factor vector. This is something that you'll keep using almost on a daily basis, and this is really, really important because it allows you to define groupings. So for example, if you have done an experiment, then a group can be a control group versus a drug treated group, right? So if you want to organize your data in two groups, control and drug, then a factor vector will be something that you'll be using, right? Because you'll be able to say what belongs to control group and what belongs to a drug group, right? So let's say that we can define a factor vector in a different way. So let's say that we have a bag of red, green, and blue ball, and we remove 10 balls from them. Okay? And what we get is the first three are red, next three are blue, and then we get two of green, 6, 7, 8, and then we get one more red and one more green. So let's say that we want to put this in a vector format where we can keep the groupings in an organized manner, right? So we can say my factor. So now what we can do is, so first of all, it will of course have to be a collection of alphabets, red, blue, and green, right? Because that will define the color. And then to tell R that it's not just a simple collection, but a collection which has to be organized in a group, we have to say factor. Right? So this whole collection has to be enclosed in a function called factor. So now we can either type red 3 times, then blue 3 times, then green 2 times. We can type that out, or we can use another helper function which is called replicate. So you can search for the help pages of replicate. It's REP $REP. And it's a very simple function, as the name suggests. It takes 2 arguments. The first argument is a scalar, so an element, and the second argument is times. Yeah, so it's very simple. It just repeats the same thing as many times as you want, right? So instead of typing red 3 times, we can say replicate red 3, right? Right. So now we will get the word red 3 times, so we don't have to type them out. Also, it's a bit less error prone. Then we say replicate blue again 3 times. Then we say replicate green times. Just make sure that the number that you want to replicate is within the bracket of this replicate function, not outside. Otherwise, it will throw an error. Best is to actually use the arguments that it has presented. Then it's a bit less error prone. And we have red and green. Right. So all of these alphabets are enclosed in a collection, and they are enclosed in a function for factor to tell that they're organized in groups. R will guess the groups itself. So you don't have to actually specify the groups. Whatever are the non-unique values, they become part of one group, right? Right. So see, I have made a mistake. So green should be in quotation mark, because anything that's not in quotation mark is a variable, and there is no variable called green. So we put it in quotation mark, right? And then we see what my factor is. You see, it is a collection of 10 strings. So it's a character vector. But additionally, it says here levels: blue, green, and red. And the reason why it's organized in blue, green, and red is because R will organize your groups alphabetically. So that's why it became blue, green, and red. Although, if you look at the help page for factor, you can actually define your levels in an order, and you can even define whether this grouping set is ordered or not, and then R will actually take the order that you give it. So if you want to put red as the first group, you can do it. Yeah, so it is possible to do it, right? So you can define the levels or the organization of the levels how you want. If you do not define it, then by default it's alphabetical. Yeah. Okay. Yeah. So the quotation mark is now fine, right? Yeah. So this is just a helper function that will help you. That will avoid a lot of typing. Also makes the code a little bit better. And there is also a replicate.int, which is just for replicating integer numbers. Yeah, a bit more faster, I think. Right? Yeah, it says here replicate.int and replicate underscore length are faster, simplified version. Right? So so this becomes your factor variable. And let me just check if there was anything else that I wanted to cover today. Yes. The advantage of factor variable is that it allows you to look at some characteristics of this grouping very quickly. So one of the function is table, and table will count how many elements exist belonging to each uh, group, and it will help you print them out. So it will do the counting for you. So we have 4 reds, 3 blues, and 3 greens, right? And let's say if you want the proportions of elements in each group, right? So proportions would be how many elements exist out of total, right? So you need a number for the total, right? And as we have discussed before, to get a number of total elements, we can use this function called length, which gives us the number of elements. Right? And when we divide it, so the table provides us number of elements in each group, and then when we divide by the total number of elements, we get the proportions. Right? We had 10, so it's just divided by 10. You can easily use these things for plotting. So let's make our first plot today. So let's make a pie chart. Right? And it's very simple. So pie chart is made by the function pi, PIE. And to the pie chart, what we will pass is this table. Yeah. So we'll pass it the proportions, or not the proportions, but actually the number of elements in each group. It will calculate the proportions. It will know what the groups are and how to order them. It, of course, doesn't really know that blue is blue, the color blue. So it will put some random colors. But when you make this plot, it very easily makes the 3 groups, defines the 3 groups, or separates the 3 groups, and then makes the pie chart for you. Right? So this is a really good advantage of having a factor vector, because R knows that in a factor vector, the groupings are defined. So the elements are organized in discrete groups, and it can use this to its advantage for plotting. And we'll also see later on how it really helps in making bar plots, how it really helps in um, making analysis very fast, statistical analysis. Right? So I think this was more or less uh, yes, what I wanted to cover from last time. So if there is no if everything is clear about the four kind of vectors, then we can move forward. But I wanted to go through them again because these are really the fundamentals of all coding. So these vectors you will find in all languages. They are not specific to R, and once you get a good hang of them, then it's uh, the progress can be much faster. Yeah. So the thing that we really want to do today is to look at two-dimensional objects. So right now, until now, we were only considering one-dimensional objects, right? So all vectors are one-dimensional. So we have nothing that is two. So now we go to a two-dimensional object. And the two-dimensional object that we will be looking at, I just need to zoom out a little bit more, is this data set called iris. So iris is a very old data set. It was generated in 1936, and it's a data set that has that was actually used by Ronald Fisher well, in a way, to make the first let's say machine learning program. So he made a discriminatory analysis. So this data set has four calculations. It calculates the length and the width of the petal and the length and width of the sepal. And Ronald Fisher used these four calculations to make a predictive algorithm, so as to classify uh, the three different species based on these four features, right? So the whole question was, given these four numbers, can you actually predict what plant it is? Is it Setosa, versicolor, or virginica, right? So this is a very classical data set, and what it has is it has 50 samples, so 50 plants for each species, and for each plant, four features have been measured. So features are something that you observe, so some kind of calculation that is being done. And in this case, the four features were the length and width of sepals and petals, and all the numbers are provided in centimeters. Yeah. So how do we get this data into R? Well, R actually comes with a lot of data sets, so you do not have to get them. And a lot of these data sets are essentially provided so that you can play with them. You can have you can do your analysis. You can learn how to analyze things. And so let's look at them. So if you do library data sets, right? Actually, you do not have to do library data sets because it's already always loaded. But if you do question mark data sets, then we'll go to the help page for the dataset package. And this will say that if you want to look at all the list, then to run this command. So let's run this command. And here you'll find that these are all the data sets that come preloaded with R. So you do not have to download them. They are available for you to play around with. A few of them are like RS is always here. It's a very classical data set. There are a few other ones like uh, usage of internet. Uh, I think there are a few biological ones also, like DNAs, assay, and all these kind of things. So if you're interested, have a look at all of these different data sets, and they're always loaded, so you can look at them, play around with them, right? But today we'll be focusing on this iris data set. So what is the iris data set? So if you have not typed any command, it's completely fine because everything is preloaded into R. You don't have to um, make a library or something. It comes pre-installed. All you have to do is to just write the name of the data set called iris. And if you press enter, you will see that it will show you the data set. It will show you the complete observations. So these are the same observations that were made in 1936. So they have all remained the same. And you will see that you come with you get these 4 features, which are sepal length, sepal width, petal length, and petal width. And you get a 5th one, which is the species. And for the first 4, they are numbers. For the last column, it's a character, right? And if you look at a data frame, so this is our first 2-dimensional data structure, right? So in this case, now you have rows and you have columns, right? You have 5 columns, 4 which are numbers. So these have something that is quantitative, and the last column which has characters, which is qualitative, right? So this is not a quantity, right? So how generally data frames are organized in R, or how people most of the time organize them. Uh, and it also makes R very powerful because most of the functions are written for a certain organization of data frame. And in our session 4, we will go into details on if your data set is not organized in a way that makes R very useful, how do you change the organization of the data frame? So that will be session 4. But just to give you an introduction, this is called a tidy organization. And what is a tidy organization? Means that each column has all the calculations related to a feature. So they are organized, all the things that you observed related to one feature or attribute are all organized in one column, right? So in one column, you have all the calculations for sepal length, all the observations for sepal width, and so on and so on. And in each row, you have one case or you have one sample. So this is going to be one plant, then the second plant, third plant, fourth plant, and so on and so on, right? So this is how um, if you organize your data set in this way, then R becomes very powerful, right? And we'll have another example related to biological later in the session on what it means to have a non-tidy data, right? But let's go ahead right now with this. So the first thing, what do you do once you have a data set is to not do anything with it except just to explore it. So just get a know-how about the data set. And that's actually sometimes very important because uh, just looking at the data set sometimes gives you a lot of insight into the data set without directly jumping into plotting or directly jumping into statistical analysis, right? So R actually lets you explore data sets very, very quickly. So the first and a very useful function to explore any data set is this summary. So if you have the function summary and you give it a data set, uh, it can also be a numerical vector. It doesn't matter. It can also be any vector, but it works very nicely with data sets, data frame. Sorry. So summary, the name of the data frame. Then it gives you a very concise insight into the data set. So for all the columns which are quantitative, it will give you the distribution. So it will give you the central tendencies, which are mean and median, and it will give you the ranges. So it will give you the minimum value, the maximum value, first and third quantile for every column which is quantitative. Plus, for any column that is qualitative, it will assume that it's a factor, right? And it will group them. And it will tell you how many elements belonging to each factor exist. So this is similar to table, right? So it has made a table for all the quantitative columns. So what it tells us immediately is that, okay, there are 50 elements belonging to each of the 3 species, right? And these are the different kinds of mean medians, right? So this is, okay, this is some number, right? Um, right. And another thing that it actually helps you judge is that another thing that you can actually see that each column has a column name. Sorry, I missed that. So each column has its own name, right? This is not an element, right? So you can call each of the column with a very specific name. They have to be unique, so a column name cannot be repeated, right? So the first column is called sepal.length. So it has a name, and this is called the name of the column, right? And this becomes very helpful later onward. So this is the first exploration that you can do. You can just say summary, and you will get some quantitative data, some qualitative data. Next thing you can do is, I'll just make my plot. You can just say plot and data frame. Don't worry about what needs to be plotted against what or any sort of things. You can just call the function plot with a data frame, and R will make you a plot grid. And this is also sometimes very, very helpful. Yeah. So in the plot grid, what R does is it takes each column and plots it against every other column one by one. So it will make a grid. So the grid will be column multiplied by column. So it will have all the columns on one axis and also all the columns repeated on the other axis, right? And this is particularly useful because you can see some sort of trends here. So you can see that, well, sepal length and petal length. So for this particular graph in the middle, on the y-axis you have sepal length, on the x-axis you have petal length. Well, these two things seem to correlate, right? We don't really know which of these data points belongs to which groups. We'll come to that later, right? But already you see that there is some correlation in this observation, right? You also see that this looks very discrete. It just seems like either all the values are 1, 2, or 3, right? It's not a continuous distribution. And that's because it's also plotting the qualitative value species, and it's plotting species as 1, 2, and 3 because remember, factors are treated as numericals behind the scene. So each level or each group is a number. So the first group is 1, 2, 3, and so on and so on, right? So so for R, each group of species is a number 1, 2, and 3, and that's why these do not look very continuous, right? But even though they do not look very continuous, you can already see that if you look at petal width, you already see that one of the species has a very low petal width on average, right? And then another one is sort of in the middle. The third one is a little bit higher, right? So you can already see that there is some variation that's that's easily detectable between the three species, right? Um, so actually, I do not know if I had zoomed on this plot, so I do not know if you actually saw the zoom, but I hope that uh, this plot was it was easy to look at this thing, right? So initially I was talking about this plot, so you can see that sepal length and petal length are correlated, and then for species they are discrete. Yeah, I think the zoomed plot, when I zoomed the plot, it didn't really appear on YouTube, so sorry about that. Yeah, but it's very easy to explore your data frame with these two functions. And another other functions that can help you explore your data frame are a function that will show you part of the data frame. So you see, when you printed out the full data frame, it prints everything, and the whole thing can be pretty big. So sometimes you don't really want to look at all of it. So what you can do is head. So head is a function that will just print out a few elements uh, at the top. So the top few elements. And as an exercise, maybe you can check how many elements it prints out. It's always the same number of elements, and to check that, you always have to go into the help page of the function. So question mark head takes you to the help page, right? Yes, I just saw, yes, correlation coefficients are available, and we will go to that. Somebody just commented. Yeah. So it says in head the default n is 6, right? So it's always the first 6 elements. Yeah. So for a data frame, it will be the first 6 rows, and if it's a vector, then the first 6 elements of a vector, right? So you can change it. Let's say if you want to look at the first 10 elements, so n equals to 10, right? So n is going to define how many elements you are going to see. So here n, a single integer, if positive or 0, size of the resultant objects, right? So if I want to see the first 10 elements, I'll say n equals 10, right? Now I can see the first 10 elements, right? You can also do tail. So tail is going to give you the last, the end, right? And when you look at tail, you look at the end of it. So again, it's the last 6. Yeah, again, the tail function is similar to head. Tail x n equals to 6, right? So this can tell you, it can show you, it can easily show you, give you some insight into the data frame, right? Because you can look at it quickly, and with summary, you get a very nice idea about which are quantitative, which are qualitative. Plot helps you plot the different quantities, right? And so the next thing is that we were using length to know how many elements existed in a vector, right? So vectors were one dimensional, so it had length. So for two-dimensional objects, what you have is dimensions. And to look at dimensions, you need dim. So dim is the function, right? So if you were to do length on a data frame, it will give you the number of columns, or the number of features, or the number of observations that you have taken, right? So the length is actually how many unique observations are present in the data frame, right? But to actually get at the total dimension, the total it's a two-dimensional data structure, you have to use dim. And always, for any kind of data frame in R, this is very important, the first number is always the number of rows, so the number of samples, the number of cases, and the second number is always the number of observations. Yeah, this is always the case. So the first number will be 150 because it's number 150 cases, and the second number will be how many unique features were measured, right? Or how many features were measured. Well, the columns will have to have unique names, right? So this gives you an idea of how your data set is. So now what we will do is I'll actually jump a little bit, just so that it becomes a little bit more interesting. And let's just make the first thing that we always want to make with data, and make a box plot. Yeah. So and this is where the name of the column will become useful. So we'll just make a box plot, just so that it's kind of exciting, and then we'll come to the little bit of the tedious and foundational part, which is subsetting and everything. But first, let's make a box plot for sepal length, let's say, versus species. Right? So we want to see the distribution of how sepal length is changing, but after grouping, right? So for each group, what is the distribution? Well, as you can imagine, the function for making a box plot is box plot, right? So it's pretty simple. And once you go into the help page, what you will see is that you can call the box plot with the formula. And this is what makes a data frame organized in a tidy format so very powerful, because we'll see what this formula means. So a formula means that you can define y, so something that you want to put on your y-axis against a group, and that's it. That's all that you have to do. And the second thing that you have to define is your data. So you have to give it just two inputs. Your first input will be your data, right? What do you want to plot? Where do the values come from? And the second thing that you have to give it, what should be on the y-axis and how should it be separated? What will define the groups, right? So I'll just go through this one by one. So if we say box plot, so it says what should be on the y-axis. Well, we want sepal length on the y-axis. How do we tell it that we want sepal length? We just write the name sepal length because sepal length is the name of a column. So we can write the name of any column and R will recognize or R will check for that name in the column, right? So if it's not a column name, then of course R will not know what you want to plot. But as long as it's the name of a column, you can just write it. Unfortunately, there is no auto completion here, and the spellings have to be correct because there is no auto completion because R doesn't know what data you are trying to access right now, right? So you just have to type it out. If you want, you can also copy paste, right? So on the y-axis, you need sepal length, right? And on the x-axis, you want to separate sepal length by groups, and the name of the column that has your groupings is species, right? So this is what you want to plot, what will be on the y-axis and how it will be separated on the x-axis. And the second thing, so just for making it much more clear, I'll say formula. You don't have to type formula because it will match the arguments. So, but I think as a habit, it's better. And then data equal to iris. So what R will do is it will look at this data frame. It will search for these two in the column names. So they have to match the column names. Then it will take this column, it will put it on the y-axis, and then on the x-axis, it will separate it by species. And that's it. The box plot is done, right? And this is the real power of having a factor variable and a tidy data frame, right? So all the observations were in one column, all the groupings were in another column, and you just had to tell it, plot me this versus this, take all this information from this data set, and that's it. Now, we can go into detail into how to make the plot more beautiful. So if you also want to change the color or you want to change what it's written here, but I will leave that to you because you can look at the help page into how to do that, because that depends on uh, at the end of the day what you want, and also because there will be two sessions dedicated to only plotting. So in those two sessions we will go into more details as to how to give them color and um, all these kind of things. So those will be, I think, session number 5 and 6, right? But this is as simple as uh, it's as easy as this to plot things in R. Literally, once your data is in a tidy format, um, and calling a plot is this much easier, right? So we can also, so as an exercise, just make a box plot for petal length versus species, just as an exercise. I'll just wait for like 10-20 seconds. If you want to pause it, you can pause the video. Okay. So I think it was pretty obvious how to change it. So petal length is again the name of a column, right? And if it's a name of a column, then you can just specify it and say compared to species, or group them by species, and get this data from this data frame. Yes. Vivian asked, what is the range of the box plot, and what is this? You'll find all of this information in the help page for box plot. So it tells you exactly what it plots, and also you can change the range. So if I think it's the first to third quantile, but if you want to change it, everything can be changed. You can see that there are so many attributes. Yeah. So yes, so as you have said, it's a quantile, and then you also get the outliers. But you can see all this in the help page. Let's see where it says. Mm, yeah, if the range is positive to the most extreme point, no more than. So I think it's, yeah. I don't remember at the top of my head what exactly is it, but I think it's uh, first to third quantile or something like that. Yeah, but you can read all about it in this help page, and you can also change them, so it depends on you. Yeah. um, so next thing is, uh, let's say you do have a data table, but you don't have a calculation, or a measurement that already exists, or you want to make a measurement. So let's say that what we want to plot is the ratio of sepal length to petal length, and then we want to group them by species, right? So we want now the ratios. Let's say that what we need is a ratio of length to petal length plotted versus species. So this is something that you want, right? So how do we add this information, and how do we plot it? So one thing is that actually, before we go here, we have to learn a little bit about subsetting. So it was a little bit of a jump. So we'll go to subsetting first, and then we'll come back to this question, because let's say this is our aim. So we want to take the ratio of the two things, and then we want to plot it against species, right? So how do we reach here? So to reach here, first we'll have to know how to obtain the values of sepal length and petal length, and then to divide them with each other, right? How do we obtain these values? So to obtain these values, you will of course have to do what is called subsetting, right? So subsetting means to extract part of either of any data structure, right? And subsetting always is working with brackets, with square brackets, right? So last time for vectors, we were subsetting with square brackets, and we were just putting a number or a range, right? So for example, if we go back to our random numbers, I forget what the name was. Yeah, random number, right? So we had 10 numbers. So if we wanted the first 5, then we would put square bracket and then tell it 1 to 5, right? And that would mean that you get the first 5. Now subsetting a data frame is working exactly like this, but there is one very major difference. And the major difference is that in a bracket, you will have to specify 2 numbers, because it's a 2-dimensional data structure. So here it was 1-dimensional data structure. So you just give it a collection of numbers, a linear collection of numbers. But here it's 2 dimensions. So you have to subset, you have to tell R which rows to subset and which columns to subset. That's easy. That it's as easy as that. And always the row comes first the row is before the comma and the column comes second. So which row to subset, that information you will put before a comma, and which column to subset, this information you will put after the comma. Enclose them in a square bracket, and if you have your data frame, then you can subset it. So this is subsetting for 2 dimensions. If you have written a line, but you want to comment it, right? So either you can go here and put the hashtag, or on Mac, it's Command Shift C. So this is the shortcut for commenting it. So anywhere on the line you are, you just put Command Shift C and it makes that line a comment. Also, if it's a comment and you want to decomment it, it will work the same. So Command Shift C will decomment a line, right? So right. So let's say we want to subset sepal length. So this is the first column, and petal length is the third column, right? So as you can imagine, it's pretty easy. So let's make a new variable, get sepal length, and we will subset our data frame iris. Now we have to tell it that we want all the rows, right? We want the complete information. We don't want to miss any information. You don't have to specify a range in that case, and this is something that R allows you to do. All you have to do is put nothing in that position, and nothing in a position means everything. So it's, yeah. So if you do not specify, then it means give all. Yeah. So if we do like this, right? So we put no number before the comma. So before the comma is which rows do we want, or which observation, which cases do we want? We want all of them. Then we put 1. That means we want the first column and the first column only. So we do not want any other column. So now we have extracted all the sepal length numbers from this data frame. We have taken it out. Now, just think, what kind of data structure will this variable be? I'll just wait for 5 seconds, right? You have subsetted a 2-dimensional data structure in which you chose only one column. So will you get a vector, or will you get a 1-dimensional data structure or a 2-dimensional data structure, right? So if you think about it, what you will get is 1-dimensional data structure, because you have only picked up one column, right? So, and you can see it here. It's a number which goes from 1 to 150, right? Yeah. And if you print it out, you will again see that it's just a vector with all the numbers, right? And you can also see if this is correct by looking at its dimension, and its dimension is null, because it's not a 2-dimensional data structure, so it doesn't really have a dimension. What it has is a length. Right? So all vectors have length, only 2-dimensional data structures have dimensions. So its length is 150. So the shortcut for assignment operator is Alt minus on Mac. I do not know about Windows. So and let's say if we now want to get the petal length, sorry, so we say get petal length. Then what we want is the third column, right? This is column number 1, 2, 3, and we need the third column. So now we have the sepal length, we have the petal length. Now we can make a ratio. So we can say get length divided by get, sorry. Right, so we got all the sepal length, we got all the petal length, and we just made a single ratio. We store them into a new variable, right? So now we have our ratios. But remember, now this thing is again a vector, right? And it's not in a format, it's not part of the data frame, the original data frame. And so it's the formula function will not really work here, right? So we can make it part of the data frame, yeah, by just calling, sorry, before that, I think we have to just see how to subset a column. So we'll just wait for 1 second before we make part of the data frame. So see, right now we were subsetting based on a number. So we were giving it a number, and that was the column it was subsetting. So we were telling it, take all the rows and the first column, right? This is kind of prone to error, or it's not very intuitive, because the first column doesn't really give you any information. We knew that the first column was sepal length, but if you just read this, it's not very intuitive, right? It says, okay, iris square bracket first column, but you have to know that the first column is sepal length, and only then you will understand that we put the information in this variable. So what R allows you to do is to subset a data frame column with a shortcut. And this shortcut makes it really, really intuitive. And that is that you just have to write the name of the data frame, put the dollar sign, and then you can choose. R will itself suggest to you all the options, and then you can choose which of the column do you want to choose, right? So data frame dollar column name, and that is why column names are so powerful, right? Because you can subset them like this. This is exactly same as iris minus 1. Right? So instead of saying I want to subset the first column, I can call the column by its name. Only thing is, subsetting is not happening by square brackets, it's happening by dollar sign. And in this way, you also always get all the rows, so you get all the values, and what you get is again a data a vector. Yeah, and this is a shorthand way of writing, but actually the most preferred way of writing. And why is it more preferred way of writing? Because let's say you got this iris data set from somebody else, like from maybe 2 or 3 sources, and for some reason your columns were shuffled, right? So somebody has put sepal length as first, somebody has put petal length as first, and all that, right? In this case, it can happen that your code doesn't really run for all purposes, because the first column maybe is not sepal length for everybody, right? But as long as people have given the column name as sepal.length, it wouldn't matter what position is it in, right? So this way the code is a bit more universal in a sense. As long as the name of the column is sepal length, R will do the search itself and give you that column. Yeah, and this makes also writing a little bit more intuitive, right? And so let's say that I want the ratio again. So I'll just say that we want to calculate the ratio again. Uh, I'll make a new vector, and this also makes it easier to write code in a little bit shorter format. So you want the ratio of sepal to petal, right? So all you have to do is to make the data frame color, you choose the column that you want, divided by iris dollar, right? So I hope that this is making is clear. Yeah, I'll just go through it once more time. So if you want to subset a column, you can either subset it using square brackets, in which you specify the column number, or you can subset a column by using this dollar sign where you specify the column name, right? And this is a little bit better way of subsetting, because then you do not care about the column number. You do not have to search for it. R will do the search for you, right? And in this way, you can again get the same ratio, but it just reading wise, it's a bit more easier, right? So we also did the exact same thing before. So we first subset the first column. We then subset the third column. So we got all the readings of sepal length. We got all the readings for petal length. We made a ratio. T is missing. Yeah. Sorry. Right. But we can also do the same by just saying the name of the data frame, dollar, the column name, right? And it will make the ratio between two columns. The next thing is, this not only gives you the information, it also allows you to make new columns. So it also allows you to expand your data frame, right? Can I put the name of the column inside the bracket? Yes. So Barbara asked, can you put the name of the column inside the bracket? Absolutely. What you can also do is you can go here. Now you want to put the name sepal length inside the column, inside the bracket. Because you want to put the name, it has to be in double quotation. But what you can do is you can go inside and you can press tab, and actually it will also suggest to you the different names of the column. And when you press on them, it will already put them in quotation mark. If you manually type your quotation marks, then if you press tab, then it actually goes to the directories. So then it doesn't give you column names. So just go inside, press tab, and it will give you, it will let you autocomplete. So this is also completely fine. All these three are exactly the same. So iris, in this case, iris 1 is this, and iris dollar sepal length. All these three are equivalent. They all give you the same result, right? And now the next thing is, we want to add new columns. So we want to make this ratio part of the data frame, right? So all we do is, very simply, we just say ratio is equal to petal length. I just giving it a small name, yeah. And then we can assign a value to it, right? So you can either get the value or you can assign a new value. Just be careful, if there is already an existing column with that name, and if you assign some value to it, R will overwrite it and not give you any warning or error. Yeah, so this depends on you, that you make sure that if you want to add a new one, then you give it a new unique name. If it's a name that is matching the previous one, then it's just overwritten. There is no warning or no error, right? And then we assign this value here. Okay, I had just not run this command, right? And I'll just write in a shorthand manner. So yeah, this is just it's exactly doing the same thing, but it's doing everything in one line, right? So what we have done here is, we want to make a new column which contains the ratio, right? And so we just say iris dollar, this new name of the column that we want, and then we say that it has to be a ratio of values from this column against values from this column, right? And it could be any operation. It need not be division. It could be addition. It could be anything, right? And this is going to give us the ratio. So we can see if it did that when we print the first few elements. Now you see that instead of having 5 columns, there is one more column that has been added up, and that might be the ratio. So the first number should be 5.1 divided by 1.4. So let's see, 5.1 divided by 1.4. So it's 3.6. So it's matching exactly, right? So it has done an element by element, a case by case division, and printed it here. Yeah. So I hope that this is clear. Actually, for the next session, we will go through subsetting again. So if something is not clear, just email me or send it to me. But this is the most important concept in R, and this is what makes R very powerful. Yeah. And once you have the ratio, now we can make our box plot just like before. So in box plot, it will not auto-complete your column name. So better is maybe to copy paste. We'll use the formula variation, right? So we will have the ratio compared to species, and our data will be iris. So because we made a new column in iris, now the iris data set has a new 6th column and it's saved in it, right? So it's so now iris has expanded, the whole data set has expanded, right? And so that's why now it can get this value from the new expanded data set, right? We just saved it into the same name. So once we do that, we get our new plot, which now has the ratio of sepal length to petal length, right? So this is the advantage of having column names. This is the advantage of using column names. And this is the advantage of this makes these kind of things much more faster, right? So I'll show you one more thing which I think most of you are interested in, and then we'll go for maybe 20 minutes of basic foundational work. So how exactly is subsetting working and all of that kind of thing. But before we go there, one other thing which I think most of the people ask is statistical analysis. Right? Well, you can plot these things, but are they statistically significant from each other, right? So we have 3 groups. So the best way is to do ANOVA, right? So that is what we want to do. And the way to do ANOVA in R or is to first actually make a model, a linear model, and then to use the linear model to get the parameters. So it's actually a 2-step thing, and this is just something that how R does ANOVA, right? So first you have to make an ANOVA model. So it's also, this is something that also I had to Google it, but it's just a 2-step process. And once you know these 2 steps, then it's pretty straightforward. Yeah. So to make the ANOVA model, the function is AOV. So we can also check what the function does. So this AOV function fits a variance model, right? And again, you call it with a formula, and then you give it a data. And I think if you followed how to make the box plot using formula, then this seems pretty intuitive, right? So let's say we want to know if the distribution of sepal length is statistically different between the 3 species, right? So I'll give you 20 seconds to make the model, to make the ANOVA model, and then call. So here you will see how to use it. So after you make the ANOVA model, all you will have to do is to call summary ANOVA.model, and this will give you your statistical test. So I'll give you 30 seconds to do it yourself. Yeah. Uh, use the formula way to see if sepal length is statistically different based on species. You don't have to see on the screen what I'm typing if you want to do it yourself, or you can even pause. Yeah. So the formula function is working exactly as before, right? So we want to know if sepal length is statistically different between species. Right? All you have to do is, well, tell it that I want to compare a quantity, sepal length, grouped by a quality, species, which is also a factor variable, and this becomes the advantage of a factor variable, right? It's a grouping, and get this information from this data structure called iris. For Mac, no, I do not have a shortcut. It's on top. It's uh, so Adria asked what's the shortcut for this tilde. So it's also called tilde, this thing, or the approximation sign. Um, so it's on the left. It's on top. It's on the top of the button left to the one. So it's underneath the escape key, and it's with shift. At least on my Mac. So I'm not really sure if somebody knows how to type this tilde with Mac. Just comment or let me. Yeah. So right, so now you get your formula here, and then you just have to call a summary. So you first, so it first fits a model, and then you just have to call summary model. It's just how it is working in R. Okay, so for Mac in French, it's Alt N. Okay, well, for Spanish, too many languages. Yeah. Okay. And so what it tells us is that it's highly significant, right? Uh, so the difference between the species is highly significant, right? And then you would want to do pairwise analysis, right? So you would want to compare uh, one with each other and to see which ones are statistically significant, right? And a pairwise comparison after ANOVA is 2Ks honest significant differences. Yeah. And for this it's very simple, because you have to just give it the argument which is already the fitted model, right? So the argument is actually the fitted model that comes from ANOVA. So we will do that. Right. So here is the function, right? And x equals to the fitted model. So this model we have already fitted, and that's why actually in R you first fit the model, because then anything that you'd want to do downstream you can do with the model. So once we do that, right, then it will do pairwise comparison between all the groups. So if there are 3, then it will be 3. If there are 4 or 10, it doesn't matter. It will do pairwise comparison between each and every group, right? And it will give you the p-value here, right? And this is a really straightforward way, right? It's simple to read. right? So you want to compare your sepal length grouped by species. This is where all the data is coming from. And it's very similarly how it's working with plots. It's working with many other things, right? So this kind of formula notation makes it very clear. It depends on column names, and it depends on your data being tidy, which means that all of your observations should be in the same column, right? So I think we will work on this more and more, right? Um, but for now, we'll go back to something more fundamental, and that's how to actually subset a data frame. I mean, we already looked at how to subset columns, but I'll just go through it a bit more formally. So, and then we will have one more exercise at the end. We'll take one more case example. Yeah. So subsetting a data frame, as I said, it's very simple. So you have the data frame, you specify which row you want, and then which column you want, right? If you do not specify, it means all. If you specify, then it will give you that. You can also specify by number or by name. So by number or name, both is fine. But if you specify by name, then it has to be enclosed in the quotation marks, right? Or only for columns, but not for rows. You can specify by the data frame, name of the data frame, dollar column. So these are the two ways. So let's just try out a few examples. So let's say I want the first 3 rows and the first 2 columns, right? So first 3 rows and first 2 columns, right? So I can tell 1, 2, 3, comma, right? This would mean the numbers 1, 2, and 3. And because it's before a comma, it means it specifies the number of rows or the position of rows. And then the first 2, so 1 to 2, right? So here now we are subsetting, and we are subsetting both rows and columns within a range. So our result will also be a data frame, because the result will be again 2-dimensional, right? Because it will have rows, it will have the first 3 rows from iris data set, and it will have columns, the first 2 columns, right? So here is our result, a shortened one, right? Next, we can just specify one number or one name. And so let's say if we just specify 1, 2, 3, and if we do not specify the column, then it will be the first 3 rows, but all the columns, right? And now the new iris also has this ratio here. Yeah. Similarly for the columns, if you leave out, don't type anything, right? So this would mean give me the first 2 columns, but give me all the rows. Yeah. Now these are simple ones. We will also do one with the name, right? So we can give it 2 names, length and sepal dot width, right? So you can not only pass it one name, but you can pass it a vector of names, a vector of column names, right? And it will make a subset for by selecting just those 2 one. This thing won't work for dollar. So when you do subsetting by using this dollar sign, you can only get one column, right? So here, so there is nothing like iris dollar c sepal dot length. This thing, there is nothing like this. The dollar notation will only and always only give you one column, right? But here, this is how you can get multiple columns by name, right? So this is an error. Yeah. So how to get multiple columns by name? The dollar sign is always only going to work to subset one column error, right? Um, so you can also call um, data frames by rows. You can also give names to rows. And actually, when you look at most of the bioinformatics, they not only have a column name, but they also have a row name. So in most of the time in bioinformatics, the column name is your sample. So your gene expression data at least is uh, organized as uh, each sample or each cell, let's say, as one column, and then each gene as one row. And therefore, the name of the row is mostly the name of the gene. Now, you see that iris doesn't really have a row name. It just has these numbers, but we can give it a row name, right? So how to get the names of the columns and the names of the rows? It's by these two functions, call names and row names. Very simple. So call names iris gives you the name of the columns, and row names data frame gives you the name of the data frame of the rows. If there is no name, well, then it's just numbers, right? But you can also use the same function to specify it. Again, you have to be careful because it overrides. It doesn't ask you. Uh, it doesn't asks you. It doesn't give an error or a warning that it already has a name, right? So if you override a previous name, it just overrides it. So let's use our paste function from before to paste row 1 to 50, right? So if we do paste, let's do paste 0 because it's not good to have space. Okay? So row to 150. Does this, I'll just go through this again. So paste 0, right? It's going to combine these two characters together, right? So the result of paste 0, row 0 to 150 will be row 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 until 150, right? And this is what we are going to assign as a row name. So iris has 150 rows. So if we assign this as a row name to iris, then the names of the row will be changed from by with this row 1 to 150, right? Um, this is okay way to do it. But if you make a mistake and if you write a wrong number here, so let's say if I write 125, then it will give an error. And what it will tell me is that the number, the names that you're trying to assign doesn't really match the dimension, right? Because we only have 125 characters here. Yeah. So a better way is to actually uh, use this other function, which is called n row iris. So n row is a function which will give you the number of rows, right? And n call is a function that gives you the number of columns. Yeah, so this is some functions to get more characteristics. So I'll just go through this a bit. I'll just repeat what happened here. So you have these two helpful functions which are very similar to dim. So dim iris or dim data frame gives you two numbers. The first number being the number of rows, and the second number being the number of columns. If you are just interested in the number of rows, you can use this function called n row, number of row. Or if you're just interested in the number of columns, you can use this function called ncall, right? So now we want to rename uh, the rows of this data frame with row 1 to 150. But instead of specifying 150, we can just specify n row iris, and this r will replace this with 150. And this is a bit more safer because here there is much less chance of making an error, right? Because this iris is 150, sure, but maybe somebody changed it, removed 20 values, right? So then it becomes 130. So instead of you making the calculation, you let r make the calculation, right? So 1 to n row data frame will go from 1 to 150 in this case, because that is the number of rows. And then if we paste it with row, then it makes that kind of vector, right? So now let's specify with the row name as this. And now if you look at the new data frame, now you see that instead of a number, every row has a name, just like every column has a name. And now you can subset the rows based on name, but not with the dollar sign. The dollar sign is only specific to column. The rows cannot be subsetted with the dollar sign. You have to use the square bracket. But what you can say is row 1, let's say row 9. So all I'm doing is putting a comma, going into this round bracket and pressing tab, and it will give me if I type R also, then it will give me all the different options for the names, right? Because now rows have names, so it can give me options. And row 128. So now I can also subset the data frame based on the names of the row. Yeah. And comma nothing. So that means give me all the columns, right? And this is the result. So now you see you get row 1, you get row 9, all the rows that we called by names, row 128, and then we get all the columns, right? So this is also subsetting a data frame by names. So iris does not come by default with the name of a row, but we can assign it the name of a row, and then we can use it to subset, right? And the last thing, so it's already 2 hours, but I think it would be good to just continue for 20 more minutes since we are on the topic of subsetting. Because we'll go through subsetting again next week. So, but I'll just introduce you that. So just like in vectors, you could subset by position where you gave a number here, and also by condition, right? Using logical vectors. So here also you can subset by logical vectors. So you can subset by some sort of comparison. So this is conditional subsetting. So let's say that I'm only interested in getting the results for Setosa. I'm not interested in the other species. All I'm interested in is having the results for this one species, right? So that would be subsetting, right? I want to extract some information from the whole. I want a small part of it, so I have to subset it. So I'm only interested in getting the information from Setosa. That means that I'm interested in all the rows, right? So I'm interested in all the rows for which the name of the species Setosa, right? So let's just go through it logically. And this is the last thing for today. So I want to get all information for Setosa plants. What it equates to is that I want to subset the rows for which the species equates to Setosa, right? So we can do it step by step. First, we can find out in which of the rows the species name is Setosa, right? So we can make a logical vector is dot Setosa. That's just a variable name that we made. And here we will compare if the name of the species is Setosa. Yeah. So first of all, how do we get the names of the species? Well, we have to get the species column, right? So we have to subset. So that's the first level of subsetting. So we will say iris dollar species, right? So this subsetting will give us the column species, which has 3 values. It has Setosa, Virginica, and versicolor, I think. I forget. Anyway, right? But if we make a comparison like this, right? Let's type out one by one. So what is iris dollar species? So iris dollar species has three, is a vector, first of all, because you have subset, a column, a single column. So it makes a vector, one-dimensional structure. And it has three values, setosa, versicolor, or virginica. And it's a factor, right? So which has three groups, right? Now, if we make a comparison with setosa, then element by element, R will compare the value of this vector with this input that we have given. And if it matches, it becomes true. If it doesn't match, it becomes false, right? And we can save the result here in a new logical vector. So now, right, now this new vector that we have defined is logical. We can also check if it's really logical using this function mode. So it is logical, right? And now we want all the information for which this condition was met, right? So we want all the rows, right? And I can imagine that it's pretty obvious now how to subset something for rows, right? Where you only want rows, right? So this says that give me all the rows which will match this based on this logical vector. And in this logical vector, it's true if the species name matched with setosa, otherwise it's false, right? And give me all the columns. And you can see already this thing is of length 50 now. Now we only have 50 rows, right? And for all the species, we only have setosa remaining. So the other two have been removed, right? So this is conditional subsetting, where you actually provide a condition that is going to make a subset of the data frame. So for the very last thing, what we now will subset is we want to obtain all the plants for which sepal length is greater than 3. And so obtain all plants for with sepal length greater than 3, right? So we want to get all the plants. Not only that, we want to get the distribution of species. So how many plants from each species have sepal length greater than 3? So that's our question, right? So if you want, you can pause here and try to work this out by yourself. I'll go through it step by step. So first we need to make a comparison, right? So we will make a new logical vector is sepal length greater than 3. Yeah, it's just the name of a logical vector. And in this case, just like last time, we are going to get all the sepal length and we are going to make a comparison. Right? So then we will know which of the plants had sepal length greater than 3, right? We will have this as a logical vector. Yeah. And now we can select these plants. So we can make a subset, and instead of just plotting the data, we can store it into a variable. That's because we can then do more analysis based on this, right? So first we will subset this data frame. We want all the rows, so we want all the plants that match this condition, right? So the subsetting is on rows, but we want all the columns. Yeah. So this becomes a much smaller data set. So let's see how this data set is. So when we see this data set, first of all, let's see what is the dimension of this data set. Did we actually lose any plants or did we select everything? Right. So first we look at the dimension. Well, it's actually we selected everything, right? So clearly this is not a good selection, right? So it has everything. Let's see. Okay. Simple width. We'll keep on going. Let's make a selection at 5. Yeah. So we want to select all the plants with sepal length greater than 5. Okay. Now we lost, we only have 118 plants, right? We lost 32 plants. So there are 32 plants for which sepal length is less than 5, right? So we have now our smaller selected data set for which this condition is working. And now we want to get the distribution of species, right? First of all, the information of species is in the column species, even in this new data frame, because we asked it to give us all the columns, right? So if we want the distribution of species, all we have to do is to call table for the new data frame. Sorry, but only for the column species, right? So we extract the information about species from this selected data frame, and since it's a factor, we can go to the function table, and now we see that only 22 plants in Setosa match this criteria, 47 in versicolor and 49 in virginica. We can again make a pie chart of this using the function pi. Right? And I think the plots are really, really small, but it's giving me error because my plot is too big. Yeah. So this is the kind of plot you will get. Right. So now we have made a selection based on some criteria on a feature, right? And we use this to obtain some additional information, right? To make this kind of pie chart, right? So I hope that this was understandable, comprehensible. How did we reach from this selection to this pie chart, right? So it's all about how do you subset your data, right? And using this concept of subsetting to extract information in a step-by-step manner. So first we subsetted the whole data frame based on the criteria that the sepal length should have been greater than 5. Then we subsetted the new data frame only to extract information on species, and that we use to make first proportions, right? Because it's a factor, and to also make the pie chart, right? So once you have this concept of subsetting clear, actually then it only depends on the kind of question do you have. So you just do it step by step, and most of the time it becomes very simple, right? And once you get good at it, so I'm just going to type out the command as to how it could be written uh, in just one line, right? So so this is the one line version of everything that we did beforehand, right? And if you think that this is too confusing, then yes, it is too confusing. And I would not advise to code like this. I would actually advise you to code in a step-by-step manner, which also makes the code more intuitive, more easy to read, more easy to comprehend. So, right, but just to go through this, right? So we take our data frame, we subset the rows. Now we know that the new data frame will have all the columns. So it will have a column called species. So we already subset it, and then we pass it on to table and pie. Yeah. Yes. So somebody asked if other methods than ANOVA are present, and they are present. Yes. Yes. So for the next session, I'll not go through the summary because I think maybe it's this presentation will be uploaded on the. It's all actually already uploaded on GitHub, so you can have a look at it, right? But all I'll say is that get familiar with the formula notation. It's really powerful if your data frame is if your data is tidy, and um, the next session will actually be on how do we make this more readable? How do we make this subsetting even more easy to look at or easy to comprehend? And for that, we will be using tidyverse. So I think some people did have problem with um, installing tidyverse. So we'll sort them out. But this is what we did today in a way, right? To obtain our data. So either you can do it step by step, or you can do it in one line, right? Not very easy to read, not very easy to comprehend, and this is too lengthy. And next week with tidyverse, we'll make it look like this, in which each step is one transformation, and it's easy to follow. So you know what is happening in each step, and it's much less coding, or at least the writing part is much less than before. So this is the kind of uh, analysis that we will do next time. Actually, it's not a new analysis, but just a different way of writing. It makes it much more human readable. So the whole point of the tidyverse is to make code human readable. Yeah. So for the next session, this is what we'll do. So we'll essentially repeat the same thing, but with a new language, with a new tool, right? And just as a last thing, what is tidy and what is not tidy? So this will be the last slide. So we do, it's very simple, a normal experiment to have a control and a drug situation, let's say. And let's say we are measuring some quantity. I mean, let's just say number of cells, right? So in an Excel, we have a habit, including myself, to write our results in this way. So we have a condition of control, and then we have a condition of drug, and these are the cells that we observed, let's say in different animals in the control condition, and these are the cells that we observed in different animals in the drug condition. This is not a tidy format, because what you have made is you have made observations on number of cells, but this observation you have divided into multiple columns, right? So one observation has been split based on groups. What R likes to work with and is this tidy format in which each observation is one column. And it's a little bit difficult to get used to this format, to be honest. It also took me some time to get used to this kind of format, because this is the more intuitive way. This is how we record our results in most of the time. But this kind of structure allows faster processing and allows much more efficient processing and code writing, as we saw today, because it allows formula notation. And in actually our fifth session, we will see how to convert this format into this format from an Excel sheet. So you can save all of your data in an Excel sheet in this format. We'll use R to read that Excel sheet. We'll do the conversion from this format, what is called a wide format, to a long format in R, and then you can use this format to do your analysis. So if you really like this format, the wide format, and this looks not so intuitive to you, don't worry about it. You can store all of your data into this format and then use R to convert and do the analysis. But R likes to have the long format or the tidy format where each observation is one column. So you combine everything in one column, and then other parameters, other observations go into other columns, right? So this is the tidy format. So that's it. It went maybe 20 minutes more than expected. And this summary is, the summary slides will be online. And as I said that on GitHub page now, there is going to be information on all the sessions. So I will email a few people, but I don't want to spam. So just make sure that you look at the GitHub page. And the next session is planned for Thursday at 5 p.m. Brussels time, so Thursday same time. And for the next session, we only have one agenda, and that's to make this one line of code human readable, to make it more intuitive, to make it more easy to read, to also to make it more easier to code. That's the whole agenda for the next session. So with that, yeah, thank you. And then, okay, so somebody says that the long format is used by all statistical software. Yes, but not with Excel. So, and because most of the people are using Excel, it's to me it was counterintuitive. It took me some time to get used to it. Are we using transposition to convert Excel file? We will have a full session on that. So we will read the Excel file in any format you want, wide format or long format. So you can save all your data in the wide format, and then R will allow you to make it into long format and then do the analysis. Yeah, and Yura has made all the notes and she will upload it on GitHub. So thank you, Yura. Those notes are fantastic. And so hopefully we'll see you next time for Tidyverse. And the session after that is reading Excel files, and then we'll come back to plotting again. Okay, so thank you and bye-bye.